You are standing on a planet that you think is safe, but in reality it is not. And if you look closely enough, you will see that the numbers are telling a very different story. The global average temperature has risen about 1.1 degrees Celsius since the pre-industrial period, according to reports from the Intergovernmental Panel on Climate Change. And that is not just a small number, but a sign that the entire energy system of the Earth is changing. Every year, humans emit more than 35 billion tons of carbon, altering the way this planet retains heat, exactly as Svante Arrhenius described more than a century ago, meaning this is not speculation, but physics in action. NASA satellites show that Greenland is losing about 280 billion tons of ice each year. And if you put it all together, you will realize this is not normal at all, because the current century is not a period of stability, but a planetary scale test, and you are right in the middle of it. If you continue to fast forward the timeline just a bit, only a few hundred years, you will begin to see the things you thought were the most sustainable start to disappear. In about 100 to 300 years, many coastal cities like New York City could face frequent flooding as sea levels rise from about 0.5 to 2 meters, according to scenarios from the Intergovernmental Panel on Climate Change. And that does not require a sudden disaster, just the physics of water and temperature. The steel in the buildings you believe are solid will begin to oxidize and weaken over a few centuries if there are no humans to maintain them, while concrete will gradually crack over thousands of years due to repeated freeze-thaw cycles, a slow but unavoidable process. If you go further to about 10,000 years, even structures designed to last a long time like Hoover Dam will be significantly eroded by water and time. While one of the most persistent traces of civilization is not architecture but nuclear physics, with isotopes like plutonium-239 having a half-life of about 24,100 years, still continuing to exist as a faint signal that we were once here. At the same time, if atmospheric KO concentrations drop low enough over time, the orbital cycles known as Milankovitch cycles could trigger a new ice age. And at that point you will realize that the Earth does not need humans to recover in the way we imagine. It simply returns to its own new energy balance state. And when you look at all of this at once, what remains is not the buildings or cities, but only a thin layer in the geological record, where our traces are compressed into a very small signal in a story billions of years long. And if you continue to push the timeline even further, beyond all ordinary human intuition, you begin to enter a phase where the Earth is no longer a familiar place, but becomes a truly dynamic system. In the range from 10,000 to 100,000 years, small changes in the planet's orbit around the Sun and the tilt of its axis, what we call Milankovitch cycles, will continue to adjust the amount of energy the Earth receives. And what is remarkable is that these changes are very small geometrically, but can lead to very large climate consequences, because the Earth's climate system is a non-linear system. If the conditions are right, this planet could enter a new ice age in about 50,000 years, and that is not a hypothesis, but something that has happened many times in geological history, with the most recent peak about 20,000 years ago, when the global average temperature was 5 to 8 degrees Celsius lower than today. And you must understand that this drop was not simply colder weather, but a complete restructuring of the planet's surface, when giant ice sheets, kilometers thick, could expand from the two poles to cover much of North America and Europe, crushing the current landscape and creating new geological structures. When water is locked up in these ice masses, global sea levels could drop more than 120 meters, exposing vast areas of land that today lie under the ocean, connecting continents and completely changing the world map you are familiar with. And if you stand in that time frame, you would not recognize this planet anymore. But even such slow and large-scale changes are not the whole story, because when you extend the time scale to hundreds of thousands to millions of years, you must begin to account for rare but extremely destructive events. Things that almost never happen in the human lifetime, but in geological time are almost certain. And one of the clearest examples is asteroid impacts. Earth has a history of being bombarded by objects from space, and the most prominent event we know of is the Chicxulub impact about 66 million years ago, when an asteroid about 10 kilometers in diameter slammed into what is now the Yucatan Peninsula, releasing an amount of energy equivalent to billions of nuclear bombs generating shockwaves. Global earthquakes, giant tsunamis, and a massive amount of dust thrown into the atmosphere, blocking sunlight for months or even years. The consequence was not the direct impact killing everything, but the collapse of the climate system and food chain. When photosynthesis was interrupted and temperatures dropped sharply, leading to the extinction of about 75% of species on Earth, including the dinosaurs. What is important here is not whether such an asteroid could happen, but that the probability of such events increases over time. And when you extend the timescale far enough, hundreds of thousands to millions of years, a major impact is no longer a rare possibility, but becomes statistically almost inevitable. Because space is not empty, but filled with fragments of matter moving at speeds of tens of kilometers per second. And when you combine these two factors, the slow but powerful climate cycles driven by orbits and the sudden but devastating events from space, you begin to see a completely different picture of the Earth, a planet that is not stable at all, but constantly oscillating between different states, sometimes changing over tens of thousands of years and sometimes in just a few days. And what makes this remarkable is not the level of danger, but its certainty. Because while you may live your entire life without seeing an ice age or a large asteroid, in the longer timescale, these events are not exceptions, but a normal part of the system. And that leads to a rather difficult to accept but entirely consistent conclusion with physics. That the stability you perceive today is not the default state of the Earth, but only a brief moment between continuous fluctuations. Beyond the fluctuations of ice and the impacts from space, you begin to see a deeper layer of change, slower but more persistent than anything else, and that is biological evolution. According to what Charles Darwin described, evolution is not a process with a goal or a pre-designed plan, but simply the result of natural selection, where individuals better adapted to the environment are more likely to survive and reproduce. And the important thing is that this process does not head toward any point of perfection. It only responds to what exists at each moment. If you look at humans themselves, you will see that Homo sapiens only appeared about 300,000 years ago, an extremely short period compared to the millions of years of geological history, which means what you call modern humans is actually just a temporary moment in a much longer flow. When you extend time to millions of years, mutations in DNA, which occur randomly in each generation, would accumulate, and although each individual change is almost insignificant, over hundreds of thousands or millions of generations, they can lead to profound differences in morphology, function, and behavior, creating forms of life that you would hardly recognize as connected to the present. The environment in which these organisms live is also not static, as you have seen. The climate changes. Ice advances and retreats, sea levels rise and fall. Continents drift at a rate of a few centimeters per year. And occasionally events like asteroid impacts or large-scale volcanic activity will disrupt the entire system, creating evolutionary shocks, where most species disappear and the few survivors thrive in the new conditions. In Earth's history, more than 99% of species that ever existed have gone extinct, and that is not an exception but the basic rule of life, because any species is bound by the environment to which it is adapted. And when the environment changes enough, the old adaptation is no longer effective. You may think humans are special, and to some extent that is true. But from an evolutionary perspective, we are still just one species affected by the same rules as all other species. If humans still exist after millions of years, then it is very likely that they will no longer look like they do now, not only in appearance, but also in biological structure, cognitive abilities, and how they interact with the environment. Or it is also possible that another species, originating from us or completely independent, will replace us, just as mammals developed and took dominance after the dinosaurs disappeared. What is interesting is that all of this does not require any intention from nature. There is no plan, no final goal, only the simple rules of genetics, variation, and selection operating continuously over very long periods of time. And when you look at this picture, you begin to realize that the question, how long will humans exist, is not the right question, Because in the timescale of millions of years, no species keeps its form or role unchanged. The better question is, what form of life will continue to exist under the new conditions? And the answer always changes with the environment. Therefore, when you look at the future of the Earth at this scale, you do not see a world where everything stays the same, but a continuous process of replacement, where species appear, develop, and then disappear, making way for what comes next. And when you go beyond the millions of years of biological evolution, you will begin to see that not only life changes, but the very foundation that life depends on is also not standing still. The surface of the Earth you are standing on is actually not a solid, motionless block, but a system of tectonic plates drifting on the hot molten mantle below, and this process occurs continuously at an average speed of only a few centimeters per year, a number so small that you cannot notice it in your lifetime. But if you extend the time to 10, 20, or 50 million years, these small movements will accumulate into enormous changes, enough to completely redraw the world map. The clearest example is the Atlantic Ocean, which is expanding at a rate of about 2 to 3 centimeters per year due to magma continuously rising at the mid-ocean ridge and pushing the plates apart, meaning the Americas are slowly separating from Europe and Africa. And if you could observe this process in a time-lapse spanning tens of millions of years, you would see the continents drifting like giant icebergs on water. But not all plates are separating. In many places they collide with each other. And one of the most prominent examples is the Himalayan mountain range, where the Indian plate is pushing into the Eurasian plate at a rate of a few centimeters per year, causing this mountain range to continue rising, even as erosion by wind, water, and ice simultaneously wears them down, creating a dynamic equilibrium between building and destruction. This shows you that even the structures that seem the most permanent are only temporary on long time scales. When you extend the view further, you will see that the oceans are not fixed entities either. They can expand and then close again, a process that has happened many times in Earth's history, through what is called the supercontinent cycle, where continents merge into one large mass and then split apart, a cycle lasting hundreds of millions of years. About 300 million years ago, all the continents once merged into a supercontinent called Pangaea, and before that, there were other supercontinents like Rodinia or Columbia, which shows that the current structure of the Earth is not a special or stable state, but only a phase in a long repeating sequence. Modern geological models predict that in the future, the continents could converge again into a new supercontinent, sometimes called Amarsia or Pangaea Proxima, and when that happens, the consequences are not only changes in the position of land masses, but also a complete restructuring of the planet's climate system, because ocean currents will be altered. The distribution of heat between the equator and the poles will be different, and the interior regions of the supercontinent could become extremely dry and hot due to being far from the ocean. At the same time, the edges of the continents where plates collide will become regions of intense geological activity with volcanoes, earthquakes, and continuous mountain building, while other areas may become relatively stable. If you look at all of this at once, from the expansion of oceans, the rising of mountains, to the merging and splitting of continents, you will realize that the Earth is not a static foundation, but a system that continuously reconstructs itself through deep physical processes within. This has a very important consequence, that the world map you are familiar with the shapes of the continents, coastlines, and the positions of countries, is not something with long-term meaning, but only a temporary snapshot of an ongoing process. If you could look at this planet in a time-lapse spanning tens of millions of years, you would not see a stable world, but continents drifting, colliding, breaking apart, and reassembling like giant puzzle pieces continuously being rearranged. When you continue to fast-forward the timeline by another tens of millions of years, the slow movements of the tectonic plates you just saw will no longer be just isolated changes, but will begin to converge into a much larger outcome, which is the formation of a new supercontinent, a state that the Earth has gone through many times in its history. About 300 million years ago, all the continents on this planet once merged into a single block called Pangaea, and this is not speculation but confirmed by much geological evidence. From the astonishing fit between the east coast of South America and the west coast of Africa to the similar distribution of fossils on continents that are now far apart. What is important is that Pangea was not a special event, but only a phase in a long cycle where continents merge and then split apart. And this cycle lasts hundreds of millions of years. When you extend time forward, modern geological models predict that the current continents could converge again into a new supercontinent, sometimes called a Masia or Pangea Proxima, which could form in about 50 to 100 million years from now, depending on how the plates continue to move and collide. When that happens, you will not only see changes in the position of land, but will also witness a complete restructuring of the planet's climate system, because the way heat is distributed on Earth depends heavily on the positions of oceans and continents. One of the most important features of a supercontinent is that its interior lies very far from the ocean, meaning moisture from the sea has difficulty moving deep inland, leading to vast arid regions stretching thousands of kilometers. And because there is no water to moderate temperatures, these areas will experience extreme temperature swings between day and night, between summer and winter, creating a harsh environment in which most current life would struggle to survive. At the same time, the merging of the continents will also completely alter the structure of the oceans, potentially creating a super-large ocean surrounding the supercontinent. And this change will disrupt ocean currents like the Gulf Stream, which currently play an important role in transporting heat from the equatorial regions to higher latitudes, keeping the climate in many parts of the Earth relatively mild. When these ocean currents are interrupted or changed, the entire climate system will be restructured, leading to some areas becoming hotter, others colder, and regions once rich in biological resources potentially becoming barren or uninhabitable. In addition, the edges of the supercontinent, where plates collide with each other, will become regions of intense geological activity with volcanoes, earthquakes, and continuous mountain formation, while the interior regions become relatively stable but harsh in climate, creating a clear differentiation between areas on the planet. This also directly affects life, because ecosystems will have to adapt to completely new conditions, and many current species may not be able to survive in such an environment, leading to waves of extinction and the emergence of new life forms better suited. If you compare this world with the current world, where continents are dispersed and oceans cover most of the surface, you will see that the difference is not only geographical, but in the entire way the planet operates, from climate and oceans to the biosphere. Areas that were once seas could become land. Areas that were once mild could become harsh, and familiar ecosystems could completely disappear. All of this shows that the current structure of the Earth, the separated continents and oceans distributed as you see today, is not a long-term stable state, but only a temporary phase in the planet's long cycle. When you look far enough into time, you will no longer see a familiar map, but a system that continuously reconstructs itself, where continents drift, collide, merge, and then split apart again. Here is the full, accurate, and natural American English translation of the provided Vietnamese text. No content has been added or omitted. It starts to become clear that not only the shape of the Earth is changing, but also the way this planet distributes energy, and that directly determines the climate. The position of the continents plays a key role in shaping ocean currents, and in the current world, a classic example is the Gulf Stream, a warm water current that transports heat from the equatorial region northward into the North Atlantic, helping to warm Western Europe and maintain a relatively mild climate for its latitude. When continents move and merge into a supercontinent, the oceans are restructured, straits close or open, and currents like this can be weakened, redirected, or disappear entirely. When that happens, the entire planetary heat distribution system changes. You have to understand that climate does not depend only on the amount of energy received from the sun, but also on how that energy is distributed. And the oceans are one of the most efficient heat transport mechanisms. When this mechanism is disrupted, temperature differences between regions increase, leading to extremely hot areas and extremely cold areas, instead of the relatively balanced distribution we see today. In the context of a supercontinent, inland regions can lie thousands of kilometers from the ocean, making it difficult for moisture to move deep inland. This leads to the formation of giant deserts on a continental scale, where daytime temperatures can far exceed levels you are familiar with. At nighttime, temperatures drop sharply due to the lack of water to retain heat. At the same time, changes in continental structure also affect atmospheric circulation, including global wind systems and cloud formation, which in turn impact rainfall and heat distribution. When you combine all these factors, you begin to see a climate system that is no longer stable in any familiar sense, but constantly fluctuates according to the planet's geographic structure. In addition, over hundreds of millions of years, the sun itself does not stand still. Its brightness increases very slowly but steadily, about 1% every 100 million years, which means the amount of energy the Earth receives will be greater than today, raising the global average temperature over time. The combination of geographic restructuring and the increase in solar energy can push the climate toward far more extreme states than anything you see today, with regions experiencing temperatures high enough to exceed the tolerance of many complex life forms. Under such conditions, ecosystems will face enormous pressure, and as you saw in the section on evolution, when the environment changes rapidly or exceeds biological limits, many species will not be able to adapt in time and will disappear. The remaining species will be those better able to tolerate high temperatures, drought, or extreme fluctuations. Over time, this will lead to a complete transformation in the structure of the biosphere. The familiar forest you know may no longer exist. Instead, there will be ecosystems adapted to harsher conditions, or even vast areas with almost no complex life. What is important here is that life does not control the environment, but is limited by it. And when physical conditions cross a certain threshold, no amount of adaptation can compensate. If you look at Earth's history, you will see that whenever the climate changed dramatically, mass extinction events followed, and then new species better suited to the new conditions emerged. On a timescale of hundreds of millions of years, this process does not happen once but repeats, creating a continuous chain of biological replacement. When you put all of this into one picture, you begin to realize that climate is not a stable foundation, but a variable that depends on the planet's structure and the energy source from the sun. When those factors change, the climate changes with them, sometimes in extreme ways. This leads to a very clear but often overlooked conclusion. Life on Earth does not exist in a fixed environment, but must always adapt to a changing system, and over sufficiently long timescales. That environment can become completely different from what you know, to the point where most current life is no longer able to survive. And when you look at the future, in the range of 100 to 300 million years, you do not see a familiar planet with a stable climate, but a system where temperature, moisture, and energy continuously change according to the geographic structure and the evolution of the sun. Beyond the extreme climate fluctuations caused by continental structure and solar energy, you will begin to see a slower process with far more profound consequences. The gradual decline of Kohlenstoff in the atmosphere, a seemingly minor component that nevertheless plays a foundational role for all complex life on the planet. This process is driven by a geochemical mechanism called silicate rock weathering, in which atmospheric saline dissolves in rainwater to form weak carbonic acid, which then reacts with silicate minerals in rocks, turning CO and Chi into stable carbonate compounds that are washed into the ocean and eventually deposited as limestone. This process essentially removes Sal and Wans from the atmosphere and locks it away in the Earth's crust for a very long time. What is important is that this process occurs continuously and over hundreds of millions of years. It can significantly reduce atmospheric Sal points concentrations if there is no corresponding replenishment mechanism from volcanic activity. Meanwhile, as mentioned earlier, the sun's brightness gradually increases over time, and this accelerates the weathering process because of higher temperatures and greater rainfall, creating a feedback loop in which more and more Sal is removed from the atmosphere. Currently, atmospheric CO and Pre concentration is a little over 400 parts per million. But if you extend the timeline to about 300 to 500 million years in the future, geochemical models show that this concentration could drop below the critical level for plants. And this is where things start to become serious. Most plants today use the C3 photosynthetic pathway, a biological mechanism that requires a minimum CO spill level of about 150 ppm to function efficiently. If this threshold Photosynthesis becomes inefficient or stops completely, meaning plants will not be able to produce enough energy to sustain life. When plants begin to die off, the consequences do not stop at the loss of trees, but spread throughout the entire ecosystem, because plants are the foundation of the food chain, converting energy from sunlight into a form that other organisms can use. If this foundation collapses, herbivores lose their food source, followed by carnivores, and the entire complex biological network begins to collapse in a chain reaction. You might think that some plant species could adapt by using other photosynthetic pathways like C4 or CAM, which are more efficient under low CO and CON, which are more efficient under low CO-CON conditions, and that is true to a certain extent. But even these mechanisms have limits, and if core concentrations continue to decline, there will come a point where even the best adapted life forms can no longer sustain photosynthesis. At the same time as plants disappear, the amount of oxygen in the atmosphere will also gradually decrease over time, because photosynthesis is the main source of oxygen, and this will place additional pressure on aerobic organisms, including complex animal species. During this phase, you may see a transition from a planet rich in life to a planet where only simpler life forms remain, capable of surviving in harsh conditions and less dependent on photosynthesis. What is remarkable is that all of this is not the result of a sudden disaster like an asteroid impact or volcanic eruption, but the consequence of a slow, continuous process that fully obeys the laws of physics and chemistry, in which Ca is gradually removed from the atmosphere while the sun provides more and more energy. When you look at this picture, you begin to realize that complex life on Earth does not depend only on the presence of water or suitable temperatures, but also on the delicate balance of atmospheric components, especially CO. When this balance is broken in the direction of reduction, the result is not a cooler or more livable planet, but a planet where life gradually loses its energy foundation. This leads to an important conclusion that the limits of life come not only from extreme factors such as high temperature or radiation, but also from seemingly small changes in atmospheric composition. When you extend the time scale far enough, those small changes can accumulate into irreversible consequences. So in the next 300 to 500 million years, you do not see a sudden event ending life, but a gradual decline, where plants die off, the food chain collapses, and the biosphere shrinks step by step, until only the simplest life forms remain that can exist in an environment where biological energy is becoming increasingly scarce. When you continue to push the timeline even further, beyond the point where CO drop to levels that undermine the foundation of photosynthesis, you begin to see an even larger factor gradually dominating the entire system, the star that Earth orbits itself, because the sun is not a fixed energy source but is evolving over time. Stellar physics models show that the sun's brightness increases by about 10% every billion years as nuclear fusion in its core converts hydrogen into helium and changes its internal structure. Although a 10% increase may sound small, in Earth's climate system it is a very large change because the energy received from the sun is the primary driver of global temperature. As this energy input increases, Earth's average temperature will rise accordingly, and the important thing is that this process occurs continuously over hundreds of millions of years. It is not a sudden shock, but an irreversible trend. When temperatures rise beyond a certain threshold, you begin to see the oceans, which cover about 70% of the planet's surface and play a crucial role in regulating climate, start to evaporate faster than today. This not only reduces the amount of liquid water, but also introduces a large amount of water vapor into the atmosphere. Here is a very important point you need to understand. Water vapor is one of the most powerful greenhouse gases, even stronger than comb a case, at trapping heat. That means as the oceans evaporate more, the amount of water vapor in the atmosphere increases, and as a result, Earth retains more heat, raising temperatures further and creating a positive feedback loop. This feedback loop can be described simply as follows. Rising temperature causes water to evaporate. Water vapor increases the greenhouse effect. The greenhouse effect raises temperature even more, and the cycle continues, pushing the climate system toward ever hotter states. In the period from about 500 million to 1 billion years from now, this process may not yet reach a full runaway greenhouse like on Venus, But it is enough to profoundly alter the surface environment, raising average temperatures to levels that most complex organisms cannot tolerate. You must also remember that in the previous phase, CO2 concentrations had already dropped to very low levels, weakening or destroying the ability of plants to photosynthesize. That means even as temperatures rise, the biosphere has already lost one of its main mechanisms for maintaining atmospheric balance. When these two factors combine, rising temperature and a weakened biological foundation, you begin to see a rapid decline of the biosphere. Plant species, already limited by low combinal, now face higher temperatures and water imbalance, while animal species lose their food sources and face an increasingly harsh environment. Gradually, the complex ecosystems you are familiar with, forests, grasslands, or biologically rich oceans, will shrink and disappear, giving way to simpler life forms capable of surviving in high temperatures and extreme variability. As the oceans continue to evaporate, they will become shallower and may eventually be reduced to small pockets of water or isolated saline lakes, further reducing the planet's ability to regulate temperature and making temperature swings even more extreme. When you look at the overall picture, you will see that Earth is transitioning from a planet with relatively stable climate, abundant liquid water, and a rich biosphere to a state where solar energy increasingly dominates and natural regulatory mechanisms gradually lose their effectiveness. What is remarkable is that all of this is not the result of an unusual event or a rare disaster, but the direct consequence of basic physical laws operating over a very long period, where a star gradually grows brighter and a planet responds in ways you can predict if you understand the principles correctly. And when you extend the timeline to near the 1 billion year mark, you begin to see this trend clearly. Higher temperatures, less water, a changing atmosphere, and a sharply declining biosphere, not because of a single cause, but because of the convergence of many processes, all pointing toward the same outcome. This leads to a clear but not easily accepted conclusion. Complex life on Earth is not a long-term stable state, but a temporary phase, dependent on a very delicate balance between energy from the sun, atmospheric composition in the presence of liquid water. When one of these factors changes enough, the entire system responds, leading to the decline of the biosphere. So when you look at the period from 500 million to 1 billion years in the future, you do not see a planet that remains in its current state, but a gradual yet certain process of transformation, where Earth becomes hotter, drier, and less hospitable to life. And in that process, the biosphere you know today will not disappear immediately, but will shrink, weaken, and eventually be reduced to only the simplest life forms that can exist in a world that is slowly moving away from the conditions you call habitable. By about 1 billion years in the future, the processes you have just seen are no longer merely trends, but begin to reach a critical point, where Earth's climate system shifts into an entirely different state known as the runaway greenhouse effect process, in which the accumulation of water vapor in the atmosphere causes the planet to retain ever more heat until there is no longer any effective self-regulating mechanism. To understand this, you need to remember that water vapor is an extremely powerful greenhouse gas, stronger than CO% could, at trapping heat. When temperatures rise high enough, the oceans evaporate faster, injecting large amounts of water vapor into the atmosphere. This increases the planet's heat-trapping ability, which in turn raises temperatures further, creating a positive feedback loop that you saw earlier, but now becomes uncontrollable. When this feedback loop crosses a certain threshold, it is no longer stable, and the climate system is pushed into a new state where temperatures keep rising without a strong enough self-balancing mechanism to stop it. A clear example of this exists right in our own solar system, Venus, which may have had liquid water in the past, but now has a surface temperature of about 460 degrees Celsius, because a runaway greenhouse effect occurred and trapped heat to an extreme degree. In Earth's case, as it approaches the 1 billion year mark, global average temperatures could exceed 100 degrees Celsius in many areas, meaning liquid water, one of the most important factors for life as you know it, will no longer be stable on the planet's surface. The oceans, already diminished in the previous phase, will continue to evaporate until most of the water exists as vapor in the atmosphere. When water vapor reaches high concentrations, It not only enhances the greenhouse effect, but also changes the structure of the atmosphere, making it harder for thermal radiation to escape into space. Another important factor is that when water vapor rises to the upper atmosphere, ultraviolet radiation from the sun will split water molecules into hydrogen and oxygen, and the lighter hydrogen will escape into space, leading to the permanent loss of water from the planet, a process that, once it occurs on a large scale, cannot be reversed. This means Earth does not just lose water temporarily, but loses the ability to retain water in the long term. When water disappears, the geological and chemical processes that depend on it are also disrupted, changing the entire planetary system. At the same time, the rising temperatures will make Earth's surface so harsh that most complex life forms cannot survive. And even heat-tolerant microorganisms will reach their limits, because at excessively high temperatures, biological molecules such as proteins and DNA become unstable and break down. During this phase, you no longer see ecosystems like forests or oceans or any familiar environments, but instead a hot, dry planet covered by a thick atmosphere, rich in water vapor and other greenhouse gases. What is important is that this process is not a sudden event that happens in a day or a year, but the result of hundreds of millions of years of accumulation, where each small step pushes the system closer to the point of no return. When you look at the overall picture, you will see that the transition from a habitable planet to an uninhabitable one does not require a single disaster, but only the basic laws of physics operating for long enough. This leads to a very clear conclusion that Earth's habitability is not a permanent feature, but a temporary state, dependent on the balance between energy received from the sun, atmospheric composition, and the presence of liquid water. When this balance is broken in the direction of increasing heat and water loss, the planet shifts into a state where life as you know it can no longer exist. And when you stand at the 1 billion year mark in the future, looking back at the entire process, you will not see a sudden collapse, but a continuous path leading to this state, where each step is logical, each change obeys physics, and the final result is an Earth that is no longer an environment capable of supporting life, but a hot, dry planet completely dominated by the runaway greenhouse effect state that, once reached, has no path back to the conditions you call habitable. When you move past the point where the runaway greenhouse effect has completely altered the climate state, you begin to enter a phase where life is no longer merely threatened, but truly approaches its end. Because in the period from 1 to 1.5 billion years in the future, the sun's brightness will increase by an additional 10 to 15% compared to today. You must understand that in a sensitive system like Earth's climate, this increase is not small. It is equivalent to the planet continuously receiving extra energy without an effective mechanism to radiate it back into space. As energy accumulates, surface temperatures will rise to the point where familiar conditions no longer exist, and climate models show that average temperatures could exceed 50 to 70 degrees Celsius over wide areas, a level of heat far beyond the survival capacity of most complex organisms. Because at these temperatures, basic biochemical processes begin to lose stability, proteins denature, cell membranes break down, and the reactions necessary for life cannot occur efficiently. This means the complex ecosystems you have seen transform in previous sections, from forests to oceans, will no longer be able to exist, and what remains will be limited to the simplest life forms that can tolerate high temperatures and harsh environments. Among them, heat-tolerant microorganisms, often called extremophiles, may be the last organisms to persist, because they have developed special mechanisms to stabilize their biological structures at temperatures that most other life cannot withstand. However, even these organisms have limits, and as temperatures continue to rise and the environment becomes increasingly arid, their living space will gradually shrink. Another important factor is liquid water, which is an essential condition for all forms of life as you know it, and it will become increasingly rare, because at high temperatures the rate of evaporation far exceeds the ability to condense back, and when most of the water has already moved into the atmosphere or been lost in previous phases, the remaining bodies of water will become small, isolated, and unstable pockets. This not only reduces habitable space, but also disrupts the chemical cycles necessary to sustain life, since water acts as the solvent for most biological reactions. When you look at the overall picture, you will see a gradual contraction of the biosphere, where areas capable of supporting life become increasingly rare, and are limited to the most extreme environments, such as deep underground hydrothermal vents or special areas that temporarily allow water to exist. Over time, even these places will no longer have sufficient conditions to sustain life, because factors such as temperature, pressure, and chemical composition will continue to change in unfavorable directions. What is important to realize is that the end of life does not occur as a sudden event, but as a process spanning hundreds of millions of years, where each step of change reduces the ability of organisms to survive, until only the simplest life forms remain, and eventually even they disappear. During this phase, Earth is no longer a living, vibrant planet, but becomes a nearly lifeless world where physical and chemical processes continue, but without any biological participation. This leads to a very clear conclusion that life on Earth, no matter how complex and diverse it is today, is still only a temporary phase in the planet's history, dependent on a very fragile balance between energy from the sun, the presence of liquid water, and atmospheric composition. When that balance is broken in the direction of increasing heat and water loss, no mechanism can sustain life indefinitely, and the final result is a planet where the biosphere gradually shrinks, weakens, and eventually disappears completely, leaving a world where the laws of physics continue to operate, but with no life left to experience them. By about 2 to 3 billion years in the future, the picture you just saw of a planet that is almost devoid of life will take one more step, where not only the biosphere has disappeared, but the very structure of the atmosphere itself begins to collapse in very basic but irreversible ways. When the oceans, which had already declined sharply in the previous phase, continue to evaporate under high temperatures, a large amount of water vapor will accumulate in the upper layers of the atmosphere, where it is directly exposed to intense ultraviolet radiation from the sun. Here, a very important physical process called photolysis occurs, in which water molecules are broken down into hydrogen and oxygen. This may sound simple, but its consequences are extremely profound, because hydrogen is the lightest element and has high thermal velocity, which means a large portion of the hydrogen atoms will reach speeds high enough to escape Earth's gravitational pull and fly off into space, a process known as atmospheric escape. As this process continues over hundreds of millions of years, the planet will gradually lose its water supply, not only on the surface, but throughout the entire atmospheric system. And the important thing is that this process is permanent, because once the hydrogen has escaped into space, there is no natural mechanism to bring it back on a large scale. Meanwhile, the oxygen left behind after the water is split will not accumulate in the atmosphere for long, as you might think, because oxygen is a highly reactive substance and will quickly combine with other elements on the surface, especially iron-rich minerals, forming stable oxides, a process similar to metal rusting but occurring on a planetary scale. This leads to the gradual decline of oxygen concentration in the atmosphere over time, rather than an increase. And as a result, the atmosphere loses one of the most important components that once supported aerobic life. When both water and oxygen are removed from the system, the structure of the atmosphere begins to change dramatically, not only in composition but also in pressure. Currently, average atmospheric pressure at sea level is about 1 atm, enough to maintain liquid water and support complex biological processes. But as the main components are lost, the total mass of the atmosphere will decrease, and pressure may drop significantly, altering the way heat is retained and how radiation interacts with the surface. In some scenarios, the atmosphere could become thinner and more like Mars, where low pressure prevents liquid water from existing stably, while in other scenarios, depending on the remaining greenhouse gases and geological processes, it could become thick and hot like Venus, where the greenhouse effect traps heat extremely strongly. Whichever direction it takes, the common point is that the atmosphere no longer resembles the balanced state that existed for most of Earth's history with life, but shifts to a new state where physical processes completely dominate without the regulation of the biosphere. What is remarkable is that all these changes do not require any single catastrophic event, but are simply the result of processes that began much earlier, such as the increase in the sun's brightness and the gradual loss of water. And when you extend time far enough, these processes accumulate into irreversible changes. When you look at Earth during this phase, you will no longer see a blue planet with oceans and an oxygen-rich atmosphere, but a barren world where water has vanished, Oxygen has reacted with rock, and the atmosphere has changed to the point where it no longer supports any form of life as you know it. This leads to a very clear conclusion that Earth's current atmospheric state with its pressure, composition, and ability to support life is not a fixed characteristic, but the result of a series of temporary processes. And when the underlying conditions change enough, the atmosphere will shift to an entirely different state, possibly resembling the planets you see in the solar system today. And when you look into the future from 2 to 3 billion years, you'll begin to see that Earth not only loses life, but also loses the physical features that once made it special, becoming a planet that, if viewed from a distance, might not look very different from other dry and harsh worlds in the universe, where the laws of physics still operate, but without any trace of a biosphere that once existed. By about 3 to 4 billion years in the future, you begin to move beyond the range of changes on Earth itself, and step into a much larger picture, where the determining factor is no longer the atmosphere or oceans, but the evolution of the central star on which the entire system depends, the process we call stellar evolution. The Sun, like every other main sequence star, operates by fusing hydrogen into helium in its core, and over the 4.6 billion years that have passed, a significant portion of the hydrogen in its core has been consumed. This leads to an important change in its internal structure, because as hydrogen decreases, the thermal pressure from nuclear reactions no longer perfectly balances gravity. As a result, the Sun's core begins to contract under the force of gravity, and as it contracts, the temperature in the core rises, which accelerates the rate of nuclear fusion in the surrounding layers, producing more energy. This additional energy does not make the Sun smaller, but instead causes its outer layers to expand, increasing the star's radius over time. In the period from 3 to 4 billion years from now, this process will become more pronounced, and although the Sun has not yet entered the red giant phase, it will become significantly brighter than today, with its total energy output increasing steadily, continuing the trend you saw in previous sections, but at a stronger level. This means that even though Earth has already lost its water and its atmosphere has changed, the amount of energy it receives from the Sun will continue to increase, making the planet's surface ever hotter and more hostile. Another factor that is less noticed but very important is that as the Sun evolves, it also begins to lose mass through stellar wind, where particles are blown off its surface into space. And although the rate of mass loss during this phase is not extremely large, it is still enough to have subtle effects on the dynamics of the entire solar system. As the Sun's mass decreases, the gravitational pull it exerts on the planets also decreases, and this can cause the orbits of the planets to expand gently, moving them a little farther from their current positions. However, this change is not large enough to fully compensate for the increase in energy output, and therefore conditions on the inner planets, including Earth, continue to worsen. If you look at the entire system during this phase, you will see that it is no longer the stable structure we see today, but is gradually shifting into a new state, where basic parameters such as energy output, stellar structure, and orbital dynamics are all changing over time. This leads to an important consequence. Planets do not only respond to their own environments, but also to the evolution of their central star. And when that star changes, the entire system must adjust accordingly. In the range of 3 to 4 billion years, these changes may still occur relatively slowly on the cosmic timescale, but they are sufficient to lay the groundwork for larger transformations that will occur later, especially when the Sun approaches the stage of complete hydrogen exhaustion in its core. What is remarkable is that all these processes are predicted very accurately by stellar physics, and they do not depend on any random factors, but are direct consequences of the basic laws governing the evolution of stars. When you place Earth in this context, you begin to realize that the fate of the planet is not determined only by internal geological or climate processes, but is ultimately dominated by the evolution of the Sun, a factor beyond any possibility of control. This leads to a clear conclusion that the solar system, which once seemed stable for billions of years, is actually entering a long-term phase of instability, where basic parameters change over time and trigger widespread consequences for every planet. And when you look forward from the 3 to 4 billion year mark, you no longer see a static system, but an evolving one, where every component from the central star to the orbiting planets is moving along a path determined by physics. gradually leading to larger and irreversible changes in the future. Around 5 billion years in the future, the gradual changes in the sun's structure that you just saw will reach a distinct transitional phase, where this star no longer maintains a stable main sequence state but begins to enter the red giant phase, a stage of evolution predicted very clearly by stellar evolution. When hydrogen in the core is nearly exhausted, the core continues to contract and heat up, while the outer layers expand dramatically, causing the sun's radius to increase by roughly 100 to 200 times its current size, extending out to a distance comparable to or even beyond the current orbits of Mercury and Venus. What is remarkable is that during this process, the surface temperature of the sun actually decreases compared to today, from about 5,800 K to lower values, giving it the characteristic red color. But the total energy output increases dramatically due to the much larger surface area, and it is this increase in total energy that is the decisive factor for the surrounding planets. The inner planets such as Mercury and Venus will almost certainly be engulfed by the expanding envelope of the sun, not in the sense of a sudden collision, but by being enveloped and gradually incorporated into the star's hot gas layers. Meanwhile, the fate of Earth is a bit more complex, because the sun's mass loss during this phase could cause Earth's orbit to expand, pushing it a little farther out, but at the same time, drag from the expanding gas envelope and tidal interactions could pull it closer, and the final outcome is still a subject of research. But what is certain is that even in the best-case scenario, where Earth is not completely swallowed, conditions on its surface will become unimaginable. The enormous energy from the red giant sun will raise Earth's surface temperature to levels high enough to completely melt the crust, turning the continents into oceans of lava where molten minerals flow like liquid. Every trace of the current topography, from mountains to oceans, had already disappeared long ago in previous phases. But at this point, even the solid structure of the planet is no longer stable. The atmosphere, which had already been greatly reduced and transformed in earlier stages, will be blown away or mixed into the surrounding environment and will no longer exist as a distinct envelope. Molecules will be broken apart by the high temperatures and intense radiation, and Earth's material will gradually shift into a state that you would hardly associate with anything familiar. What is important to understand is that at this stage, you can no longer speak of Earth in the sense that you know, because the physical conditions have changed completely. No liquid water, no stable atmosphere, no solid surface in the traditional sense. Instead, you have a mass of material interacting directly with a star in an advanced evolutionary state where high-energy processes dominate everything. When you look at this picture, you will see that what began with small changes in climate and atmospheric composition ultimately leads to a complete transformation of the planet, where none of the familiar world's features remain. This leads to a very clear conclusion that the physical conditions that once allowed life to exist on Earth were not permanent, but existed only for a finite period in the history of the solar system. And when the central star evolves, the entire system must change with it. At the roughly 5 billion year mark in the future, you no longer see a blue planet or even a stable solid planet, but an extreme environment where energy, heat, and radiation dominate everything. And in that environment, there is no longer any way to define Earth in terms of what you once knew, because all the familiar physical conditions have vanished, giving way to an entirely different state determined not by life or geology, but by the final evolution of the very star that created it. Following the phase in which the sun has swollen into a red giant, the fate of Earth no longer lies in slow changes, but enters a series of extreme physical interactions between the planet and the expanding gas envelope of the star. As the sun loses mass through a strong stellar wind, Earth's orbit could theoretically expand due to the reduced gravitational pull, and this is sometimes viewed as a chance for the planet to escape direct engulfment. But the reality is far more complex, because this orbital expansion does not occur in an ideal vacuum, but in an environment where the sun's gas envelope has already expanded very far. As Earth moves through this dilute but still significantly dense gas, it will experience a drag force similar to friction, gradually losing orbital energy and causing the orbit to shrink rather than continue expanding. At the same time, tidal forces between Earth and the enormous mass of material in the red giant sun will create torques that alter the planet's angular momentum, and these effects tend to pull Earth closer to the Sun over time. When these two factors combine, the chance that Earth avoids complete engulfment becomes very low, and even before that happens, conditions on the planet have already exceeded all familiar physical limits. Surface temperatures will rise to thousands of degrees Celsius due to intense radiation and the extremely hot surrounding environment, enough to completely vaporize the solid crust and any remaining material on the surface, turning the planet into a mass of molten material. What were once continents, oceans, or even the solid mantle no longer exist in stable form, but shift into a plasma or high-temperature gas state. Light elements such as hydrogen, helium, and even part of the oxygen will be blown into space by the strong stellar wind, while heavier elements like iron and silicon may persist longer, but will also be gradually dispersed as the planet loses its structural integrity. As Earth continues to interact with the expanding gas envelope of the Sun, it is no longer an independent system, but becomes part of the stellar environment, where material is mixed, stretched, and ultimately merged into the common flow of matter. In some scenarios, Earth may be pulled deeper in and completely engulfed, disintegrated by tidal forces and high temperatures, much like a solid object melting and dissolving in a hot liquid. In other scenarios, part of its material may be stripped away and dispersed into space before being absorbed, but the final result remains the same. The planet no longer exists as a distinct structure. What is important here is not the precise details of which scenario occurs, but the overall outcome that the physical conditions have exceeded the threshold at which a solid planet can maintain its structure. When you look at the entire process, from the Sun's increasing energy output, the expansion of its outer layers, to the orbital and tidal interactions, you see a logical chain, where each step leads to the next without any random factors. Earth is not destroyed in the sense of a sudden explosion, but is gradually disassembled by physical forces until there is no longer any clear boundary between the planet and its surroundings. At this point, you can no longer speak of Earth as a planet with a core, mantle, and crust, because those structures have been completely broken down. Instead, you have a collection of atoms and ions moving in a high-energy environment, where they may continue to participate in other physical processes. The final conclusion becomes unavoidable. Earth, as a planet with its own structure and history, will be completely destroyed during this phase, no longer existing in any form you could recognize. And everything that once made up this planet will be dispersed and merged into the evolving solar system, becoming part of a much larger story without retaining any clear trace of its original shape. After the phase in which Earth is disassembled and loses its planetary structure, what remains is not a complete void, but a collection of matter that continues to exist and participate in larger processes in the universe, because the atoms that made up this planet, such as iron, oxygen, silicon, and many other elements, do not disappear when Earth is destroyed. According to the basic laws of physics, especially the conservation of mass energy, matter and energy cannot be created or destroyed, but can only change from one form to another. And that means everything that once constituted Earth still exists in a different form. When the Sun is in the red giant phase and then continues to evolve, it will blow off its outer layers into space, creating a structure called a planetary nebula. And in this environment, the atoms that once belonged to Earth will mix with the Sun's material, forming an expanding cloud of gas and dust. In this cloud, heavy elements like iron and silicon may combine into small dust particles, while lighter elements exist as gas, and the entire system becomes part of the interstellar medium. As time continues to pass, over hundreds of millions to billions of years, this mass of material will gradually disperse into the surrounding space, becoming part of the environment between the stars, where it may participate in larger matter cycles. In regions of the galaxy where matter density is high enough, gravity can cause these clouds of gas and dust to collapse, leading to the formation of new stars. And in that process, the atoms that once belonged to Earth may become part of new stellar systems or even new planets. This means that Earth's material does not merely exist, but can be recycled into completely different structures, participating in a continuous cycle of formation and destruction in the universe. If you look at the bigger picture, you will see that heavy elements like iron or silicon were not created on Earth, but originated from previous generations of stars. where nuclear reactions and stellar cores and supernova explosions created them and dispersed them into space, and then they gathered again to form planets like Earth. That means Earth was from the beginning part of a larger matter cycle, and when it is destroyed, its material simply returns to that cycle. What is important here is that there is no absolute beginning or end in this process, only continuous transitions between different states of matter, from gas to star, from star to nebula, and from nebula back to new stars and planets. When you look into the future billions of years after Earth has disappeared, you no longer see a specific planet, but a network of interconnected physical processes where matter moves, transforms, and restructures according to the basic laws of the universe. This leads to a very important conclusion that the end of Earth is not its complete disappearance, but only the end of one specific structure, while its basic components continue to exist and participate in new structures. From this perspective, you could say that Earth does not truly vanish, but only changes form from a solid planet with oceans and an atmosphere to part of a cloud of gas and dust, and then possibly part of another stellar system in the future. This also reflects a deeper principle of physics. The universe does not operate by absolute creation and destruction, but by continuous restructuring, where everything is conserved at a fundamental level. Therefore, when you look back at the entire process from Earth's formation to its destruction, and then the dispersal of its matter, you see a closed cycle without a stopping point, where matter is not lost, but only changes its state and role in a much larger picture. And that is precisely why, even when Earth no longer exists as a planet, what made it up continues to exist in the universe in new forms, participating in other stories that we may not even be able to observe directly. Looking at the picture, after the material of Earth is merged into the vast cosmic environment, what becomes clear is not loss or meaningless chaos, but a deeper order that governs everything. Because every step in this entire story, from the formation of the planet to its destruction, follows the basic laws of physics, especially thermodynamics. When you look back at each phase, from climate change, ice ages, biological evolution, plate tectonics, the decline of flora corns, the increase in energy from the sun, to the runaway greenhouse effect and the expansion of the red giant sun, you will not find any step that occurs randomly in the absolute sense. Instead, each event is a direct consequence of the previous state, guided by the equations that describe how energy and matter interact. This does not mean you can predict every small detail of the future exactly, because complex systems like climate or the biosphere can be very sensitive to initial conditions. But at the overall level, the direction of the system is determined by unchanging principles. One of the most important principles in this context is the second law of thermodynamics, which states that entropy, or the degree of disorder in a closed system, tends to increase over time. This means energy tends to disperse. Structures with high order tend to break down or transition into less ordered states if there is no continuous energy source to maintain them. Life on Earth, to some extent, is a temporary way to maintain local order by using energy from the sun. But when that energy source changes, or when the system can no longer maintain balance, entropy continues to increase and complex structures gradually disappear. When you apply this principle to the entire future history of Earth, you begin to see that what happens is not a series of disconnected events, but a continuous process where energy from the sun is distributed, transformed, and ultimately dispersed into space, bringing with it changes in climate, geology, and biology. Even the destruction of Earth during the red giant phase is not an unusual event, but the result of energy in the system reaching a level where the planetary structure is no longer stable. What is important is that when you look at the entire process, you realize that the future is not something separate from the present, but an extension of it, a chain of consequences that begins from initial conditions and develops according to defined laws. If you know the current state of a system and the laws that govern it, you can predict its overall direction. And that is exactly how physics allows us to talk about the future of Earth billions of years before it happens. This also helps you understand that the concept of randomness in many cases only reflects our lack of information or computational ability, not the absence of laws. At the fundamental level, particles, fields, and forces interact according to defined equations, and from these interactions, larger structures like planets and stars form and evolve. When you look at the universe in this way, you no longer see individual events, but a network of interconnected processes where each part influences the other through common laws. This leads to an important realization that understanding physics is not only about understanding how an object moves or how a reaction occurs, but about understanding how the entire universe progresses over time, from the smallest systems to the largest structures. In the context of Earth, this means the fate of the planet is not a mystery, but a result that can be inferred from what you already know about energy, matter, and the laws that govern them. When you look back at the entire story, from the formation of the planet to its disappearance, you see a continuous logical sequence, where each step is reasonable and inevitable if the initial conditions are maintained, and that leads to the final conclusion of this section. Nothing in this scenario happens randomly in the absolute sense, but everything is a consequence of the laws of physics. From that purely physical perspective, you begin to realize something quite surprising. The feeling of stability you have about the world around you does not come from the world itself, but from the limits of your perception. Because humans live for an average lifespan of only about 70 to 80 years, an extremely short time frame compared to the geological and cosmic processes you have just seen. In such a short period, most of the planet's major changes are almost imperceptible. Mountains do not rise enough for you to notice. Continents do not drift far enough to measure with the naked eye, and the climate, although it may fluctuate over a few decades, still seems stable on a daily scale. This creates a strong impression that the world is a fixed foundation, something you can rely on without thinking. But the reality is completely different when you change the timescale. If you could speed up time by millions of times, turning each year into a tiny fraction of a second, you would see a completely different picture, where what you call stability disappears and is replaced by continuous motion. In such a time lapse, continents do not stand still but drift, collide, and separate. Oceans expand and then contract. Mountain ranges rise and are then eroded away, and ice advances and retreats like slow waves. Even the climate is no longer the familiar cycles but becomes large oscillations, with hot and cold phases alternating according to cycles spanning tens of thousands to millions of years. What is important is that all these changes are happening right now, not in some distant future. It is just that their pace is too slow compared to the timescale of a human life for you to perceive them. When you expand your view even further, you will see that even the things you think are the most solid, like rock and metal, are not truly fixed. They are eroded, recrystallized, and moved through geological cycles. The atoms in your body and in the rocks and soil around you are also not standing still. They continuously exchange energy and position, participating in chemical and physical processes. This means stability is not a real property of matter, but only a way you interpret a system that is changing very slowly. When you place this realization in the context of the entire story of Earth from its formation, evolution, decline, to its destruction, you begin to see that no phase is truly stable in the absolute sense. Only phases where the rate of change is slow enough that you do not notice it. Even the present time, which you may consider normal, is only a short interval between larger fluctuations, such as the ice ages of the past or the climate changes of the future. If you could live long enough to observe millions of years, you would no longer use the word stability to describe this planet, because everything is constantly changing. What is interesting is that your brain is designed to seek stability and make predictions, because in the short term that helps you survive. But that very mechanism also makes it difficult for you to accept long-term changes. You tend to think that what you see today will continue that way into the future, even though physics shows the opposite. When you combine this with the laws you saw in the previous section, you realize that there is no permanent equilibrium state in the universe. Only temporary states in which forces and energy achieve a relative balance for a certain period of time. When conditions change, that equilibrium state also changes, and the system shifts to a new configuration. This applies to everything, from climate and geology to life and even stars. So when you look at Earth and feel it is stable, you are really looking at a very small slice of a much larger process. If you fast forward long enough, you will see that nothing keeps its shape, position, or state unchanged. Everything drifts, transforms, and restructures. This leads to an important conclusion that stability is not a property of the world, but a perceptual illusion, a result of observing a dynamic system over a time period too short to see its changes. When you understand this, the way you look at the world begins to change. You no longer see a fixed planet, but a system in continuous motion, and that fully aligns with what physics describes, where there is no absolute motionless state, but only change occurring at different timescales. And when you place yourself in that picture, you realize that your feeling of stability is not evidence of the world's unchanging nature, but only the limit of the perspective you are using to observe it, from the realization that stability is only an illusion due to observational limits. You begin to see clearly another direct consequence. The concept of control that humans believe in also has very clear limits. Because although we can change the surrounding environment on a local scale, building cities, controlling indoor temperature, adjusting river flows, or even altering atmospheric composition in the short term, all of that still takes place within a small frame compared to the entire planetary system. Humans can slow down or speed up some processes, but we cannot stop them completely, especially when looking on timescales of millions to billions of years. You cannot change Earth's orbit around the sun in any practical way, because the energy required to do so far exceeds anything a civilization could generate. And even if you could make small impacts, the gravitational forces in the solar system would continue to adjust the orbit according to basic laws. Similarly, you cannot intervene in the evolution of the sun, a star with a mass about 330,000 times that of Earth, where nuclear fusion reactions occur on a scale that no technology could significantly affect. This shows that there are processes over which humans have no control at all, not because of a lack of intelligence, but because of physical limits. Technology can help extend life, help you adapt to harsher environments, and may even allow you to leave this planet and search for other places to live. But technology cannot change the basic laws such as thermodynamics or gravity, and it is these very laws that determine the direction of large systems. If you look at any civilization, whether hypothetical or real, you will see that it is always bound by two main factors: the energy sources it can harness and the environment in which it exists. Energy allows you to do work, maintain structures, and resist local increases in entropy. But that energy source is not infinite, and as you scale up, energy demand increases very quickly. At the same time, the environment sets limits on temperature, pressure, radiation, and resources. And when these conditions change beyond a certain threshold, even advanced technology must adapt or fail. When you place this in the long-term context of Earth, you see that humans can influence the planet for hundreds or thousands of years, but cannot control processes that occur over millions or billions of years, because those processes are driven by forces and energy on a much larger scale. Even the idea of saving Earth from future changes becomes unrealistic when you understand that those changes are not accidents that can be fixed, but the result of the natural evolution of the system. This does not diminish the value of technology or human capability, but only puts them in the proper context, where you can control a small part of the system for a certain period of time, but cannot control the entire system at all times. When you look at history, you will see that every civilization has had to face these limits, whether regarding resources, environment, or energy, and those limits ultimately shape their development and existence. In the distant future, these limits do not disappear but become clearer, because large processes such as stellar evolution and planetary dynamics continue regardless of the existence of any civilization. This leads to an important realization that control is not an absolute state, but a range, and that range is limited by the laws of physics and the conditions of the system. You can expand that range with technology and knowledge, but you cannot eliminate its limits. When you place yourself in this picture, you begin to see that humans are not the controllers of the universe, but a part of it, operating within the limits that the universe sets. This does not mean that everything is beyond control, but that you need to distinguish between what you can influence and what you cannot change. And when you look at the entire story of Earth, from its formation to its destruction, you see that there are processes humans can affect in the short term, but in the long term, the direction of the system is determined by much larger factors. The conclusion becomes clear that human control, no matter how impressive, always has clear limits. And those limits are not temporary barriers, but a fundamental characteristic of how the universe operates, where every system is bound by energy, matter, and unchangeable laws. Recognizing that human control always has limits, what is important is not to react with anxiety or pessimism, but to understand the real meaning of the entire picture you've just seen, because looking at the future of Earth over millions or billions of years is not meant to frighten you, but to put you in your proper place in the universe. When you understand that everything from climate, life, to the planet itself is the result of long-term physical processes, you'll begin to see that humans are not the center of the system, but a part of it. And this does not make you small in a negative sense, but makes your perspective more accurate. Scientific knowledge in this context is not just knowing numbers or phenomena, but the ability to understand how systems work. And when you understand that, you can make better decisions in the present, because you are no longer relying on feelings or assumptions, but on verified laws. For example, when you understand how energy is retained in the atmosphere, or how ecosystems respond to environmental changes, you can see more clearly the consequences of actions over a few decades or centuries, even if you cannot influence what happens in millions of years. This leads to an important point. The meaning of understanding the future does not lie in changing that distant future, but in shaping how you act in the present. When you look back at the entire story from the formation of Earth, the evolution of life, the phases of climate change, to the decline and finally the destruction of the planet, you see a continuous sequence where no point is completely separate, and humans only appear in a very short segment of that sequence. This often makes people feel that their existence is insignificant, but in reality it only changes how you define significant, because if you measure value by length of time, then almost nothing in the universe is significant. But if you measure by the ability to perceive and experience, then even a short period can carry deep meaning. From this perspective, the value of existence does not depend on how long it lasts, but on how it occurs within that finite time. You exist in a system where everything changes, but it is precisely the ability to understand and perceive those changes that makes your experience special. When you realize that you are made of atoms that once existed in previous stars and will continue to exist in other forms in the future, you begin to see that the boundary between you and the universe is not as clear as you think. You are not separate from the universe. You are a part of it, a temporary structure formed from matter and energy that obeys common laws. This leads to a change in how you perceive freedom, because freedom is not the ability to escape those laws, but the ability to act effectively within their boundaries. When you do not understand the limits, you may think you can do anything, but reality will quickly prove otherwise. When you understand the limits, you can adjust your actions to fit reality, and that increases the chance of achieving the results you want. This applies at every level, from the individual to entire civilizations, because every system operates within certain constraints of energy, matter, and environment. When you look at the future of Earth, you see clearly that there are processes humans cannot change, such as the evolution of the sun or long-term geological cycles. But that does not make present actions meaningless. It only defines the range in which those actions can have impact. What is important is to distinguish between what you can influence and what you cannot, and to focus your energy on the parts you can change. When you do that, you are no longer trying to fight against the laws of nature, but working with them. And this is not only more effective, but also reflects a deeper understanding of the world. When you look at the universe in this way, you no longer see it as a strange or cold place, but as a consistent system where everything, including you, has its place. This leads to an important conclusion that understanding your limits is not an admission of defeat, but a necessary condition for using freedom correctly. Because freedom does not exist in a vacuum, but within the framework of laws. When you understand that framework, you can act with greater clarity and effectiveness instead of relying on inaccurate assumptions. And when you connect all of this with the story of Earth, you begin to see that the real meaning does not lie in extending existence indefinitely or avoiding unavoidable changes, but in clearly recognizing your place in a larger process and using the time you have to observe, learn, and act in ways that align with the laws that have created everything around you. This does not diminish the value of life, but makes it clearer, because when you know that everything has limits, You begin to pay more attention to how you use your time and resources, returning to the starting point of this entire story. The seemingly very simple question of whether Earth is truly stable or not is no longer an open question, but now has a very clear answer. Because after traveling through billions of years into the future from climate change, biological evolution, plate tectonics, the decline of the biosphere, to the complete destruction of the planet, you can see that everything you are observing today is only an extremely short moment in a process spanning billions of years. The mountains, oceans, climate, and even the life that you consider normal are actually only temporary states in a system that is always changing. And if you could look far enough into time, you would no longer recognize this world the way you see it now. This may make you feel that everything becomes fragile or meaningless, but the reality is exactly the opposite, because it is precisely that temporariness that makes everything more precious. Not less, because value does not come from existing forever, but from existing in a finite period of time that can be experienced. If everything were permanent and unchanging, there would be no difference between moments, and therefore no reason for any moment to become special. It is the change, the finiteness, and the continuous transition of the universe that create meaning for your experience. When you understand that you are existing in a system where everything moves according to the laws of physics, you no longer look at the world as a static place, but as an ongoing process. And this completely changes the way you perceive your own position. Humans are not the center of the universe, but they are also not an insignificant part, because there is something very special here, the ability to understand. You do not just exist in the universe, but can observe and understand it to a certain degree. And that is not a common property of every material structure. A rock or a planet does not know that it exists. But you do, and you can look at the laws of physics, understand how they work, and even predict the future of the system you are part of. This ability does not change the final outcome of large processes such as the evolution of the sun or the fate of Earth, but it completely changes the way you experience them. Instead of being swept along by processes without understanding, you can see them as a logical sequence, where each step has causes and consequences, and that brings a form of understanding that itself has value. When you place yourself in that picture, you are no longer just a creature living on the surface of a small planet, but a part of a much larger cosmic process, where matter, energy, and information continuously transform and restructure. This is not a metaphor, but an accurate description according to physics, because the atoms in your body were once part of previous stars and will continue to exist in other forms in the future. When you look at the world in this way, you begin to see that the boundary between you and the universe is not as clear as you thought, but only a convenient classification in a continuous system. This does not erase your individual identity, but places it in a broader context where you are both a distinct entity in the present and a part of a long-term process. From this perspective, the question is no longer whether everything will exist forever or not, but what do you understand about what is happening during the time you exist? Because you cannot change the basic laws of the universe, but you can understand them. And it is that understanding that allows you to direct your actions rationally. When you combine all of this, you reach a very clear conclusion that is also very different from the ordinary view. Meaning does not lie in resisting change or trying to create permanent stability, but in recognizing that you are in a dynamic process and understanding how that process operates. And when you understand that, you are no longer just living on Earth in a passive sense, but are observing and participating in an ongoing cosmic process where every moment, no matter how small on the cosmic timescale, is still part of a larger story that you have the ability to perceive. That is not an emotional or purely philosophical conclusion, but a direct consequence of the way physics describes the world, where everything is connected through consistent laws. And when you look in that way, you do not only see Earth or its future, but the entire process of which it is a part. And you realize that your ability to understand that process is what makes your existence special in a very specific and explainable way. If you want to continue exploring the biggest questions of the universe in an easy to understand and profound way, please hit subscribe to the channel so you don't miss the next content. See you again in the upcoming journeys, where we will continue to look deeper into how the universe really works.